right, and we got almost everybody. Oh, okay, just a couple more. So, good afternoon, everyone. Hello, welcome. We've got quite the action-packed day in store. Well, I think it's action-packed. I'm going to try to convince you that it is super cool stuff. We've got crazy things going on in our problem set, and it all culminates into this great big new idea about not just finding perimeters, not just finding areas like we've been doing, but really analyzing, hey, what's going on when we adjust the shape and compare one area and perimeter to another? What's the connection there? How do they really differ? What's the relationship? We're going to uncover that a little bit today. All right. What else we got? Angel here. Update that. All right. So let's look at yesterday. Strike that. 2 days. Monday's problem set. Not that one. That's algebra. And we're going to go through the answers to the problems directly and then discuss what it is we can conclude about some of what's happening here. So, starting with level 1. Here we're just determining the perimeter of each figure shown, just basic types of shapes. Well, okay, not that basic of shapes. But one step above just ordinary rectangles. We got some funky irregular hexagons and 1, 2, 3, 4, 5, 6 septagons here, right? But it's still all the same stuff. Add up all of their sides. Make sure you include the appropriate units. This is a shorthand for inches, so you can write that either way. Number 5, recall the tetrominoes. Yeah, those good old Tetris shapes. What are their perimeters like? We know the area. I mean, it's 4 squares every time, right? So the area is consistent. But how about the perimeters? There's only 5 unique shapes. Flipping them and spinning them around doesn't change this. So 4 out of the 5 all have a perimeter of 10 units, whatever you want to measure it in. And only the square shape has a smaller perimeter of only 8. So that'd be the minimum possible. So 4-way tie for the maximum. Okay, how about rows of shapes? So a row of triangles will have a perimeter of n plus 2. For n number of triangles, you'll always have 2 more toothpicks forming the whole perimeter. So we're not counting these middle ones, just what goes around the outside here. And if you go up to squares, for n squares, we have 2n plus 2. N pentagons, 3n plus 2. N hexagons, 4n plus 2. You see what they're doing here? Within each item, we found the pattern, and now looking vertically, we find a pattern among the patterns. It's always plus 2, and it counts up n, 2n, 3n, 4n, 6n for octagons. So in general, for any m-sided polygon, it's going to be 2 less than the number of sides. Octagon has 8 sides, so we use 6. Right? M minus 2 times n plus 2. All right, and here's where things start to get interesting. We have a square and a circle, both made out of wire, that enclose the same amount of area, 18.45 centimeters squared. What the number actually is not important. The fact is we made 2 different shapes, but we gave them the same area. And now when we uncoil the wire and flatten it out, we're then going to measure the length of the wire, which will be effectively the perimeter of the shape. So we're saying holding area constant, which has a greater perimeter, a square or a circle? The answer in this is a square, longer by 1.95 centimeters, specifically given this starting area. So think about what that means about the relationship between the perimeters and areas of squares and circles in general. All right, how about scaling? What if we multiply these sides of a rectangle and make them bigger? Right? What happens to the area if we multiply both length and width by 2? We'll start with thinking just about 1. If I multiply one length by 2, I get twice as long of a rectangle. I have twice as much area. Or if I make the width twice as tall, I'll have twice as much area. But now I make the length and the width double and then double again, times 2 times 2. So for a total of times 4. Right? If I multiply both sides by 3, 3 times 3 is 9 times the area. By 10, I get 100 times the area. By any amount n, I get n squared times the area. That's the relationship between a linear versus a quadratic quantity. Okay, and then in 25, we just have some practice for perimeters and areas of triangles. For part C, since they give you an irrational there, any close enough decimal approximation is fine. They didn't tell you specifically to use 2 places or whatever. You can have more digits or round it to 17.1 if you wanted to. I would at least say if that's ever the case, don't go all the way down to 17. You got to include at least a decimal so that we know that it's not an integer value at the very least. All right, any questions from the level 1 problems? No? All right, onward to level 2. So here we go back to the ominoes now with pentominoes, 5 squares apiece. What's the maximum perimeter? Now we can get up to 12 units around our perimeter. Here is one example. There's a lot more pentominoes. I didn't want to redraw all of them. But you can imagine any of the L kind of shapes, the ones that have the square go 4 in a row and then one out here, or like 3, 2, or, adding a single bend or even 2 bends, the zigzaggy guy, still perimeter of 12. It's only this one that we can pack it down to a perimeter of 10. And if you follow that same pattern from what the tetrominoes did, what the pentominoes did, keep going out to the I guess it would be an octomino, 8 squares, you would get a maximum perimeter of 18 and a minimum of 12. And you can see, once again, so here it is all in a straight line. Again, you can bend and have right angles in there just fine, still get 18. But this is the only one that will get us the lowest 12. Look at the difference between those shapes. That will come up later. Okay. Number 8. Here is a great chance to see how perimeter and area truly change or don't change, right? So we start with our basic square. 7 by 7 toothpicks on each side, so we have a perimeter of 28 toothpick units and an area of 49 units squared. That's our baseline. From that shape, we now cut out the corners, or really we're rearranging the toothpicks. So the toothpicks that were here are now going into the square. And so this 1 by 1 square of area is no longer included. It's no longer enclosed. So our perimeter is still 28 units, but our area has dropped by 1, 2, 3, those 4 squares that we cut out. It's only 45 units squared. Now here we cut out a 2 by 2 square from each corner. So our area drops again down to 33, perimeter still the same. If you went to 3 toothpicks per side in the corner, still the same perimeter, area down to only 13 units squared. It's getting tiny. In fact, that would be the limit. We're out of enough toothpicks on the side. So in general, what's happening here? The perimeter stays constant no matter what. It's always going to be 4 times your side length of the square. But the area is decreasing as the corner squares increase in size. And if your full square has a side length of m toothpicks, and you take out a square of side length n from each corner, your area will be m squared minus 4n squared. And look at what happens to those shapes. We had this nice big square. We lose out the corners and we get into this skinnier and skinnier cross shape. Okay, so next question. Related to that, what if we stuck with rectangles? Suppose 2 rectangles both have a perimeter of 40 meters. Must they also have the same area? Try a couple of examples to test your conjecture. Well, we just saw from the toothpick thing that we can easily make shapes of different areas but with the same perimeter. So here's an example of 2 rectangles that do that. Length of 15 by 5 has a perimeter of 40. Okay, add these together and double. Multiply them to get an area of 75. Well, you could also make a 10 by 10 square. Perimeter of 40, area now 100. Aha! I got more area for the same perimeter. Okay. And then here now are some perimeter and areas of non-right triangles. Just a practice exercise there. And there's the last one, triangle C. Any questions on level 2? Okay, hang on to your hats. Level 3 is where we're going to start to see some weird stuff. So first up, the triangle versus rectangle. This one's not too weird, but might not be immediately obvious. We are told that this side ED is twice the length of CD, okay? So that means this segment CD is congruent to CE up here. Yes. And how do the areas then of this triangle compare to this rectangle? It turns out those areas will be exactly the same. Here's why. If I want to find the area of the rectangle, I'm going to multiply this side, AD, by CD, the base times height. For the triangle, I'm going to do the same thing. Base AD, so that number stays the same. But the height now is DE, not DC, and we've already established DE is twice as tall, right? So I'm multiplying the same base, but now the triangle gets twice the height. So it sounds like it's going to be twice as much. Oh wait, the formula for triangle area has a multiply by 1/2 in it. So I doubled the size, but then I still have to take 1/2 for the area of the triangle. So those two operations undo each other, and I'm back to the same original area of the rectangle. See how that works? That's kind of neat, that relationship there. Which means if you were to cut this extra triangle off, just keep it as a rectangle and cut this one off, this triangle would fit perfectly inside of this triangle, right? These two pieces here, right? What you remove from the rectangle, you still maintain, right? It's the same area. It all adds up together. I thought that was kind of cool. A neat way of thinking about things. Now, here's one that'll really mess with your head. Two coins have radii of 3 centimeters and 1 centimeter. Okay, and I could even draw those in here. Right, and what are you doing? Just want to draw one. Okay, but the point is that this larger circle is 3 times as wide as the smaller circle, right? Now we also know, since circumference is still a linear quantity, it's just diameter times pi, I didn't square anything yet, the circumference of the larger circle is 3 times the circumference of the smaller circle. So if I was to roll the small circle around the larger one, okay, not letting it slip, not letting it slide, okay, I want to pretend like this is just a bent road, and I've got my tire rolling smoothly across that surface. Okay, so it turns on itself and progresses as if these were gears and they were meshing into each other, right, ticking around. The question is, how many times does the smaller one spin around by the time it gets all the way around the big one once? Right, so by the time it gets back to this position, how many times has it turned itself upside down and right back up, and then upside down and then right back up? Right? How many times did it do that? Is it pointing in the same direction, facing the same way after all the way getting around here? You would expect that if the large coin is 3 times the width, the circumference is 3 times the distance, right? I can wrap 3 of these circumferences, and I literally could. If I was to, if these were, instead of like solid coins, these were made out of, go back to the wire of square and circle wire. If I was to cut this wire open and lay it out flat, I could take 3 of these and wrap them around this circle, and they would perfectly line up. That is absolutely true. The circumference is 3 times, so you would expect it to go 3 times the distance. But it's not. It's a fake out. The real answer is 4. The puzzling bit is, why the heck do I get a 4th rotation from this? And the answer is fascinating. In fact, there is an entire Wikipedia article about this concept. It's called the coin rotation paradox. Okay? This is fascinating. So check this out. The coin rotation paradox is the counterintuitive observation that when one coin is rolled around the rim of another coin of equal size, the moving coin completes 2 full rotations after going all the way around the stationary coin. So here's a lovely animated portion for you. So we've got the stationary coin, American quarters, tails up, in the middle, not moving. And George Washington, right, is shown there rolling up and over half of that coin. And watch his head. He does a complete 360-degree tumble. He starts face up, or vertical, right? And he ends in the same position. He's still facing the same way after only going halfway around the coin. So we can infer then, if he continues and rolls around the bottom half of the tails up coin, he would rotate around again. So he would make 2 full revolutions relative to himself, right, after making 1 rotation around the center coin. How the heck does that make sense? You would expect that they should be equal. It's a 1-to-1 ratio. Their circumferences are the same. For every amount that this rolls, this one, right, they should meet equally. Just like, two gears meshing and merging together, right? This one rotates the same amount of this one if they are the same size, right? But the problem is, if you're thinking about gears, you forget that the center coin isn't moving. Gears, both of them are moving. They're both free to turn. That's why those mesh up and they go 1-to-1. So if they are the same size, one revolution here is one rotation of this coin. But the center one isn't rotating. So in order for these to stay matched up as if they were gears, the coin that is moving has to move both circles worth, right? Think of it that way. The center one is being lazy and he's not turning. Well, then the one that is turning has to do his own rotation and travel around the circle of the stationary one. So it's doing double duty. Here's another way to look at it. This is specific to our case. What if they are not the same size? So this is just like our problem. We have one coin that is 3 times the radius of the other. What we initially think, our intuition tells us, the topmost diagram up there. And that is, you see the coin, look at that rainbow-colored circle with the arrow pointing up. Okay? And as it rolls across, okay, the arrow then points to the right, and then down, and then to the left, and then back up. Okay, so it completes 1 revolution, 2 revolutions, 3 revolutions as it rolls across this flat ground. And you can check on the colors here, right? Notice the light gray matches to light gray, and then the dark gray will land on the dark gray, and when it gets to the arrow pointing to the right, the purple lands on the purple. So after black and gray land on black and gray again, it has gone one way all the way around. And then it rolls again, twice around, 3 times around. But that's on flat ground. Look at what happens when we take that flat ground, as it were, and we bend the ground itself around into another circle. We've added an additional circle in its path, like a meta circle, right? It spins 3 times relative to the ground, but now the ground is adding a rotation relative to the open space from our perspective. You can see here where black and gray meet black and gray. This arrow, from our point of view, it looks like it's pointing down and to the right a bit. But if you were to pick that up and turn it so that the ground looks, I can't do that on here. So the ground is at the bottom, right, relative to the surface. Pretend this is like the surface, something. You are still pointing up, out, away from the surface of the large circle, just like you were here. Relative to the large circle, this arrow points away from the center of the large circle. Down here at the 4 o'clock position, the arrow points away from the large circle. So relative to that, it still has 3 rotations. We start at the top, and then at the 4 o'clock and the 8 o'clock, I'm pointing away from the circle. But the large circle adds an extra rotation because the surface itself that you rolled along also goes around a circle. So you have to add 1 more full rotation, which is why we get 4 total positions where the arrow is pointing up, right? Absolutely up in the same direction it started, not relative to the circle, but relative now to our outside perspective. You see the difference? It's a little bit tricky to wrap your head around. But it's really cool. This is a great thing you can, use to win some easy bets. Be like, take out 2 quarters, set them down, don't move them, be like, okay, if I was to hold 1 quarter still and roll the other one around, how many times is it going to spin? Most people will assume it's going to go 1 time around. Be like, no, it's 2, right? So share that with your friends and younger siblings and blow their minds. Okay, the coin rotation paradox. So with that, any last call for questions from this problem set? No? Okay, then let me give a brief introduction to problem set 2, and I will leave you on your way. Problem set 2 introduces several cool new ideas that you are free to play with, and I encourage you to further explore, such as Heron's formula. Okay? This is a crazy way to get the area of a non-right triangle that is, as you can imagine, is super useful. Right triangles are extremely common, but we have plenty of triangles that are not right triangles, and we can still find the area for them very easily without having to do the whole create an altitude and measure from the 90 degrees and make stuff up. Just from the side lengths given. There is a way to do it. It's called Heron's formula. Super useful, handy little trick, great to know. Okay. Down here, I believe we've done Sierpinski's triangle before. That's that Triforce inside the Triforce thing, right? Inside the Triforce. That guy, that's Sierpinski's triangle. Here we have Sierpinski's carpet. It's the same thing, but squares now. So that's a fun little exploration into area there. What else we got? We got atom smashers. We've got another carpeting the floor in your house. This is just great practical practice there. Level 2 introduces a funky new thing. I've not heard of this one before, Pick's theorem, which is a fun way to easily estimate area of something, especially when you can throw some grids on it and you got these irregularities. It's a quick way without literally counting all of the squares. There, and continues, we've got Oklahoma, and 48 is about area of Wyoming. You can do the same thing. And 39 is some in-depth analysis. Here we've got more tires spinning and tracks. This is a great one if you've ever watched a foot race, say the Olympics, right? The 100-meter dash, or maybe not is it the 100? You need a long enough one that they actually start looping around the track, right? This is how they calculate how to give the staggered starts, because going around the inside of the track is a smaller, shorter path than going around the outside of the path, right? So you can actually calculate that yourself here, which is kind of neat. All right, so there you are. Problem set 2. We've got still, we've got a good chunk of time. There, 15, 16 minutes now for you to work. Take it away, get started. Let me know if you have any questions. Happy to help you out. Otherwise, the rest of the time is yours.